Hi, this is K. Narsimurthy. Presently, I am working as an assistant professor in Government First Grade Women's College, Tumkur. I have been presenting lot of videos for the second semester to students of Tumkur University, and the topic and the subject which I am presenting is physics. This is my 31st video for the second semester students. So we have divided an entire semester into 60 sessions. Okay, so first 15 session makes in first unit, second 15 session will makes in second unit. Okay, like this third 15 will makes third unit, and fourth 15 will makes fourth unit. Totally 60 sessions, so has been divided into 4 units. So this is my 31st video. I mean to say this is my first video in the third unit. So I am completed the 50% of the syllabus. Half of the syllabus I have presented videos. I covered 50% of syllabus in my 30 videos. Okay, this is the first video in the third unit. I mean to say 31st video when you take overall syllabus. Okay, it's a fresh chapter for you. It's a magnetic properties of the materials. So in the first unit we discussed electrostatics completely. In the second unit we discussed the magnetostatics, and here we are looking for the magnetic properties of the material. Okay, right. Yeah, origin of magnetism. You know that the magnetic field is an area around the magnet, or a current carrying conductor will produce a magnetic field. The area around the current carrying conductor is actually a magnet. To understand the magnetic behavior of the materials will be behaving like a magnet. We are looking for how the materials are behaving like a magnet. How actually the materials, which we call it as a magnets, are behaving. So we must know the origin of magnetic dipoles of an atoms and molecules. Say take for example a magnet. So why this magnet is behaving like this? Why it is producing a magnetic field? So to know that, we need to understand the origin of this. We need to understand the behavior of these magnetic materials. So we need to understand the magnetic dipole moment of each atom and molecule. So if I take a material, if I take a magnet, it is made up of large number of atoms and molecules. So to get an overall idea how it behaves like a magnet, how it produces a magnetic field, so what is this magnetic material is, so we need to understand the origin of magnetic dipole moment in each atom and molecules. We'll still go into deep, we'll still go to the micro level, we'll go to the nano level to understand the material which is behaving like a magnet, that we call it as a magnetic material. So it is actually the electron, the orbital motion as well as the spinning motion of electrons will contribute a magnetic dipole moment of an atom or a molecule. So if I take an atom, because this material, you say it's a magnetic material which is made up of large number of atoms and molecules. These atoms consist of the nucleus, which is positively charged, and it is surrounded by the negatively charged electrons which are revolving around in a particular orbit. So these electrons, when revolving, they produce a current in a loop. This current will produce us tiny magnets. Each electrons will behave like a tiny magnet. So and it has a magnetic dipole moment, and this contributes for the magnetic moment of a material. So we need to look in a micro level to understand how this magnetic moment will arise us in a material. Right. Now we need to understand some of the few definitions regarding these magnetic materials, and the first definition which we need to know here in this chapter is the intensity of magnetization. In some textbook it is represented by the symbol I, but here I am representing it by M. It doesn't matter, you represent it by any symbol. I is better actually. So because you may confuse this M with a magnetic moment. So we'll take I always to represents the intensity of magnetization. Right. So interaction of the magnetic dipole moment of atoms and molecules with the magnetic field is what we denoted by the magnetization. Okay. So I told you this magnetic material is made up of tiny magnets, tiny dipoles. So these dipoles, these magnetic dipole moments will interact with the external magnetic field. Okay, these tiny dipoles will interact with the external magnetic field. This is what we denoted by the magnetization. Okay, right. It is a measure of, actually the definition is this: the intensity of magnetization is a measure of extent to which material is magnetized. So I am going to magnetize a material. How extent I am magnetizing a material? If I magnetize a material to a greater extent, the intensity of magnetization will be more. If I could not magnetize a material to such a high extent, the magnetic intensity of magnetization will be low actually. Okay, right. So how extent you are magnetizing a material? So it is intensity of the magnetization, which is a measure of an extent to which material is magnetized. Okay, right. Now we will write an equation for this. Now it is defined as, the intensity of magnetization is defined as the magnetic moment per unit volume aligned in a magnetic field direction. Okay. So I have already told you each atomic dipole, which are randomly oriented before, without the application of magnetic field. Each magnetic dipoles are randomly oriented. Okay. So when you apply a magnetic field, each atomic molecular dipole starts orienting in the direction of the magnetic field. Okay. They align in a direction of magnetic field. Each atomic molecular dipoles will align in a direction of magnetic field when you apply a magnetic field. Okay. So when they start aligning in a direction of magnetic field, so you find out what is actually the magnetic dipole moment per unit volume, and that will gives you the intensity of magnetization. So magnetic moment per unit volume of aligned in a magnetic field direction is called the intensity of magnetization. So numerical means in the expression I can say I is equal to m by v, or you can call it as m, which is equal to m by v. So unit of this intensity of magnetization is ampere per meter. Intensity of magnetization is ampere per meter. Suppose if I take a bar magnet of length L, and pole strength I'll take it as an M. M is the pole strength, okay, and L is the length of the bar magnet. If I try to find out the intensity of magnetization, so magnetic moment is pole strength into length. Pole strength is M into L divided by volume of the bar magnet. If I take A is the area of cross section and L is the length of the bar magnet. If I try to find the magnetic field intensity of magnetization, so it is in the numerator, it is L into M divided by volume is area of cross section into length, A into length. So L cancels. I left with an M by A, which is pole strength divided by area. So intensity of magnetization in the case of bar magnet will be the M by area. It is the pole strength per unit area. Pole strength per unit area in the case of bar magnet. Now generally if I have to define an intensity of magnetization, it is the magnetic moment per unit volume. Number of magnetic dipole moments per unit volume, which are actually aligned in the direction of magnetic field. Okay, so it is actually the extent to which material is magnetized. It is the extent to which material is magnetized. Okay, so I can take some relevant example for this. Okay, don't correlate too much with a physical example which I am taking. Suppose I am teaching in a class of second semester of 100 students. Take an example that I am teaching a class of 100 students in the second semester BSc. Now if I take 1 hour of a class, what is the extent to which I can teach the 1 hour of a magnetic materials to them? Now if I look at the extent to which the material is magnetized, some will understand 50%, some will understand 60%, some will understand 80%. Okay, so I may not reach 100% to all of them. The extent to which they understand my teaching is what the intensity of my teaching. Okay, so I can correlate this with the intensity of magnetization like this. So if I sum up all the students which are grasping my teaching, some 60, 70, 80, 90 and some 50, 40, if I take an overall thing, it could be about around 60%. So that is what actually the extent to which I am teaching, I am making the student to understand in my class. This is exactly what actually the intensity of magnetization. It is the extent to which some material is magnetized by applying a magnetic field. Right. After that, we need to understand another important definition here, which is magnetizing force, H. The intensity of magnetization we understood, which we are representing by a symbol I or M. Now the magnetizing force is represented by H. This can be defined as the degree to which a magnetic field can magnetize a material. It is the degree to which a magnetic field can magnetize a material is called magnetic field or intensity or a magnetizing force. Okay. Now how can we differentiate this with the intensity of magnetization? That's a material in which it is the extent to which a material is magnetized. This is a degree to which a magnetic field can magnetize a material. Now how much I can make the student to understand. My point of view is, if I see all the students are listening my class, all the students are looking at me, they are not looking that side, this side, so I can say that 80-90% of students are understanding my class. This is my point. This is my degree of teaching. My teaching efficiency, I think that it is 90%, but what actually the extent of this thing is reaching the student was 60%. Now the degree to which a magnetic field can magnetize a material is called magnetizing field. This is actually the magnetic force. This is the magnetic field. I am looking at the magnetizing field perspective. Their intensity of magnetization, where I am looking at the perspective of the material which is magnetized. Now how much it is magnetized, how much extent to which a material is magnetized. It is a material. Here it is the magnetic field which is magnetizing the material. So in both the cases magnetization is common. But I am looking at the material perspective, I am looking at the extent to which a material is magnetized, that is intensity of magnetization. Here I am looking at the magnetic field perspective, I am looking at how much magnetic field can magnetize a material. It's a degree to which a magnetic field can magnetize a material. The perspective is different. The student's perspective of learning is different. A teacher's perspective of looking at the student and the effective teaching will be different. So degree of magnetic field can magnetize a material and extent to which a material is magnetized, both are different. That's intensity of magnetization. This is magnetizing force. Right. Suppose if I take a coil of n number of turns having length L, and I is the current what actually the flowing through the coil, then the magnetizing force is H, which is equal to Ni divided by L. So magnetizing force will increase if there are more number of coils, more number of turns, and magnetizing force will increase if more current flows in a coil, and obviously it will decrease if there is length of the coil is more. So H is equal to Ni divided by L is what the equation for the magnetizing force in the case of coil. Right, if I write this equation in general, I can write this H equals to B minus mu naught M divided by mu naught, where mu naught is a permeability of free space. I'll come to that next. I'll define that next later. So unit of magnetizing force is ampere per meter. This is ampere per meter. You go back and look for the intensity of magnetization. It is also the ampere per meter. So here also it is ampere per meter. There also it is magnetic ampere per meter. It is all same. It's a degree to which it is magnetized. It is extent to which material is magnetized. Both are quantities are same, but the unit is same. Quantity is also same, but they are actually two different quantities. Alright. Now we look for the magnetic induction or a magnetic flux density. A phenomenon of making an unmagnetized material into a magnetic substance by the influence of another magnet or a magnetizing force with or without actually any contact. You need not make any contact to magnetize a material. It is sufficient enough you apply a magnetic force. You apply a magnetic field. Okay. This phenomena of making an unmagnetic material into a magnetic material or a magnetic substance by the influence of another magnet or a magnetizing force without any actual contact or with any contact is called magnetic induction. It is what? Inducing. We are inducing magnetization in a material. Okay, that's why the name itself called it as magnetic induction. Right. Now it is actually a measure of number of magnetic lines of forces which are crashing per unit area. It is magnetic flux per area. B is equal to phi by A. Okay, and the unit of this magnetic induction is Weber per meter square, or it is Tesla. This is actually the magnetic field. It's an intensity of magnetic field B, which is Weber per meter square, or it is Tesla. Induced. It is induced magnetic field. It's a magnetic induction. Magnetic induction. Right. You need to understand the very important constant here. It is the permeability. Permeability is a degree to which the magnetic lines of forces can penetrate through a medium. It is pertaining to the medium. So take an example of one medium. You look for the penetration of magnetic lines of forces through that medium. If the degree of penetration is more, then the permeability will be more. If degree of penetration is less through the medium, then the permeability is less. Okay, it is the degree to which a magnetic lines of forces can penetrate through a medium. Okay, right, but this epsilon is different. The permittivity is different. It is the obstruction for the electric lines of forces. Students, you need to bifurcate these two. There I am using epsilon in electrostatics. Here in a magnetostatics I am using permeability mu. The epsilon there, the permittivity, is an obstruction for the electric lines of forces through a medium. It's an obstruction of a medium caused for electric lines of forces. If more obstruction, more permeability, more permittivity. If less obstruction, it's a less permittivity. But here it is not the obstruction, it is the degree of penetration. How much magnetic lines of force are penetrating through the medium is what the permeability is. Okay, it is again a constant. It is a constant for a particular medium. It varies from one medium to another medium. Take an air. For air, permeability is constant. We call it as mu naught. If you take some other medium or a mica, permeability will be different. Okay, so it depends on a medium. Right, the unit of permeability is Henry per meter. Okay, permeability, mu is what? Henry per meter. So this magnetic induction is proportional to the magnetizing force H. Magnetic induction and magnetizing force. This force is what actually inducing the magnetic field in a material. So magnetic field is what actually, the magnetic induction is what actually proportional to the magnetizing force. Right? If more force, more magnetization, obviously. Okay, so therefore I say B is proportional to H. So B is equal to mu H. You have to add some constant, which is mu. Mu is the permeability of that medium. If mu is more, if mu is more, in a sense, the H, the magnetizing force, if you applying, will produce a more magnetizing, more induction, more magnetic induction. The magnetizing force will induce a more magnetic induction if mu is more, if permeability is more, if the degree of allowing the magnetic lines is more, then the material is magnetized to a greater extent. If I take a ratio mu is equal to B by H, permeability can be defined as the ratio of magnetic induction to the magnetizing force. B is equal to mu R mu naught into H. Mu can be written as mu R into mu naught into H, where mu R is a relative permeability, and mu naught is a permeability of free space. Now I can take an equation 1 and I can write it as H is equal to B minus mu naught M by mu naught, and if I do the cross multiplication, I can write this as B is equal to mu naught H plus M, equation 3. If I compare this equation 2 and equation 3, then mu R mu naught H is equal to, which is B, which is equal to mu naught H plus M. So mu naught get cancels, mu R H is equal to H plus M. So M is equal to mu R minus 1 into H. Okay, so I got this kind of relationship between the M and the H. Means the M is the intensity of magnetization and the magnetizing force. So now I can define the relative permeability. Relative permeability mu R is defined as a ratio of magnetic permeability mu of a material to the permeability of free space. Okay, it's a ratio of permeability of a material to the permeability of free space, which we call it as absolute permeability. So mu R is equal to mu by mu naught. This mu R is a constant and it is a unitless quantity, where mu is not a unitless, it has a unit Henry per meter. Okay, right. We'll move on to this last definition, which is magnetic susceptibility, which we represent it by a symbol chi. This symbol, which is in the bracket, is chi. Magnetic susceptibility is a property of a material which determines how easily a material can be magnetized when it is placed in an external magnetic field. How much susceptible it is for a magnetization. If material is more susceptible to the magnetization, its magnetic susceptibility is more. If a material is less susceptible to the magnetization, its magnetic susceptibility is less. How easily can be magnetized? If it is magnetized more easily, it will be more. Susceptibility is more. If more easily it is magnetized. If it is not so easily magnetized, susceptibility is less. It determines how easily a material can be magnetized when it is placed in an external magnetic field. That's a condition. So you should place a magnetic material in a magnetic field and look how easily it is magnetized. If it is magnetized more easily, chi will be more. If it is not magnetized more easily, chi will be less. Now in terms of equation, I can say this as a ratio of intensity of magnetization to the magnetizing force. It is I by H, or you can say it is M by H. So chi can be defined as the ratio of intensity of magnetization to the magnetizing force. So students, we understood all the very basic definitions which regarding to the magnetic materials. So one is the intensity of magnetization, the extent to which a material is magnetized, I, or symbol M. Second one is the magnetizing force. It is a degree of to which a magnetizing force can magnetize a material. The symbol is H. Next is magnetic induction, B. Okay, it is the extent to which a force can magnetize a material. Induce, a magnetic field is induced because of that. Now I define two constants here. One is the permeability, which is the degree to which a magnetic lines of force can pass through a material, which with the symbol we call it as mu. And a magnetic susceptibility, how easily can the material is magnetized. All definitions will regarding the magnetizing a material, but these all quantities are different. You need to understand a very thin micro line between these different quantities. Okay, so students, you go through this, you will understand these things better. And we have still more equations. M is equal to chi h. If I from equation I can take M is equal to mu r 1 minus h. So finally I got this susceptibility and permeability, relative permeability relation. Again I can say that susceptibility is a unitless quantity with that equation, because mu r is a unitless quantity. Therefore the susceptibility is also a unitless quantity. Right. These are the some of the books which I referred to. You please go through it. You will understand the basic things of the magnetic materials better. Thank you.